All right, good morning. So today I'm here with Rebecca.
Hello.
Do a little bit of tutoring. We're going to talk about stoichiometry and limiting reactant problems. Rebecca is in the honors chemistry at Carlisle High School. They've just finished up a section on stoichiometry and limiting reactants. And I'm going to kind of bridge this into the next unit, which is a section on gas laws. So I've given her a problem dealing with rocketry and rocket fuels, and we're going to use that as a limiting reactant, stoichiometry, and how it applies in density as well, which is a factor that hasn't been covered significantly in class since it was first introduced in the first month or so of class. So we're going to apply the density to figure out a problem involving rocket fuel weight and the size of the rocket fuel tanks required. All right, so with that, Rebecca,
Okay.
I'm going to have you go ahead and read the problem, and then we'll let you go ahead and start working the stoichiometry and the weight of the limiting reactants and going from there. Go ahead.
All right. Hydrazine, N2H4, was one of the first fuels used to power rockets and is still used today in some circumstances. When combined with an oxidizing agent, the mixture becomes hypergolic, spontaneously combusts, generating a high amount of heat and expanding gases that propel the rocket. NASA has a small experimental rocket with a 600.0-liter hydrazine tank. Knowing that, they need to keep the weight and size of their rocket as low as possible to maximize cargo capacity. They ask you to determine which of the two oxidizers would be the better choice to minimize one, weight, and two, tank volume required to use all 600 liters of hydrazine. The two possible oxidizers are dinitrogen tetraoxide, N2O4, or anhydrous nitric acid, HNO3.
Okay, so just as in the since we haven't dealt with density, we're going to walk through the density calculations first. We know we have a 600.0 liter hydrazine tank. So that's the first thing I want you to do is using the density of hydrazine, figure out how many moles of hydrazine are within that fuel tank.
Okay.
So we start off with the 600.0 liters.
600.0 liters.
And you remember the conversion factor? Since our density is given to us in grams per cubic centimeter, do you remember how you convert a cubic centimeter into liters?
You shift the decimal or multiply by multiples of 10. And so centi is 100. So my guess would be that there's 100 centimeters in 1 liter.
Okay. So there's actually, it's a little bit different when you're converting between a distance and a unit of volume. In this case, there's actually 1,000 cubic centimeters in every liter.
Oh wait, because there's the 3.
Yep.
So okay, so it would be then you'd shift decimal places 2 over, so it'd be.
You gotta shift it over 3 over.
3. My bad. So then it'd be 1.02 grams per centimeter cubed equals works 10200. That is correct, right? Or am I going the wrong way?
No, you're going correctly.
Okay.
So you moved it over 3 decimal places, so it's 1,020 grams per liter. And that's actually, so 1,020.
Oh, I have an extra
Yep.
0. That explains a lot.
You have 1,020 grams per liter. And just as a point of reference, water is 1,000 grams per liter. So hydrazine is pretty darn close to the same density as water is.
Yeah.
Okay. All right. So if you know you have 1,020 grams per liter, and we have a 600-liter tank, how many grams of pure hydrazine do we have?
It'd be just under. Wait, say that again.
We have 600.0 liters,
Mm-hmm.
and we know the weight per liter. So I need to know the total weight of hydrazine.
So you just divide 600 by 1020?
You have 600 liters, and each liter has 1,020 grams.
I'm still...
If you had 600 gallons of milk, and each one weighs 6 pounds, how would you get the total number of pounds of milk?
You would just divide it by, no?
If I had 600 gallons, I had to carry 600 of these things. Would I divide or would I multiply?
You multiply.
Okay.
So,
I've got 600, and each of these gallons of milk weighs 6 pounds. I'd have 3,600 pounds of milk.
Okay.
So
I don't know why I was thinking divide, because I think I just got stuck in my head. So it'd be just over 6,000. 600 times.
Go ahead and use a calculator.
Yeah, I was gonna say, like, that might take a while.
Yeah, that's a lot of zeros.
It's gonna be just over 6,000, but I'm not quite sure. 600 times 1, 2, or be 612,000. So apparently it's not just over 6,000. Whoops.
You got 600 times 1,000, so it's going to be roughly a little bit over 600,000 grams.
Oh, okay, and that's just me doing bad math.
Okay. So you got a little bit over 600,000 grams. You got how many grams do you have? 612,000?
Yeah, 612,000.
So we have 612,000 grams of hydrazine. Now, how do you convert that? That's the same process that we've already used now. So this was some new introductory stuff using density in a limiting reactant problem. That's something that you haven't done at this point.
Okay.
So now that you have a grams of hydrazine, how do you convert that to moles of hydrazine?
You use the molar mass of hydrazine, which we'd have to calculate,
Okay.
to then
So it's N2.
So N 14.01 times 2 equals 28.02, and H4 equals 4.01 times 4 equals 4.04. Add 6 0.2 created 1. 32.06 grams per mole.
Okay. So I use that from this 612,000 grams. How many moles of hydrazine do we have?
That we'd have to...
We have a lot.
Yeah, I was going to say, you have to do the whole calculation thing.
Yep, go ahead and grab the calculator.
Okay. Okay, calculator. So 32.06 for 1 times gram, probably want to into each 4 times
You have
no,
this.
I got the wrong one. I was gonna say, like, something's not right here.
You're right.
612,000 32.06 grams per 1 mole equals 1908.92 moles N2H4.
Okay, that looks solid. Looks really good. Now we have to look at the balanced reactions. And I've given you the balanced reactions.
Okay.
Okay. And really, since this is a limiting reactant problem, all we're really concerned about now is the other reactant. How much of the other reactant are we going to use? So for the first reaction of hydrazine and dinitrogen tetroxide, it is a 2-to-1 ratio. So how much of the dinitrogen tetroxide are we going to use?
Oh, we have to do... My immediately thought it would be half because it's 2-to-1.
That's exactly right.
Oh, okay.
Yeah, so if we're going to use 2 moles of hydrazine, to only 1 mole of the nitrogen tetroxide, we're going to use half as much. So go ahead and show me how much dinitrogen tetroxide are we going to use?
So is that just dividing this number by 2?
That's it.
Okay, I was going to make sure. So 190.8.992 equals 954.46 mole O2N4.
This is the dinitrogen tetroxide, N2O4.
N2O4. There we go.
Okay, now do the same calculation using our anhydrous ammonia. In this case, it's a 4-to-4 ratio. So
Or 1-to-1.
It's 1-to-1, exactly right. So that's real easy. We know we're going to use the exact same number of moles of anhydrous nitric acid as we're going to use from our hydrazine. So that's real easy, 1-to-1.
Mm-hmm.
Okay, so this one, your dinitrogen tetroxide, we need only half of the size or the amount. So now we have to answer the 2 questions. Knowing that, which one is going to minimize the weight? So you're going to use the weight of dinitrogen tetroxide, and that's 954 moles of dinitrogen tetroxide. But you have to compare that to the weight of the anhydrous ammonia, the 1,908 moles of anhydrous ammonia. So which of these 2 amounts of dinitrogen tetroxide and the ammonia, which one weighs less?
The dinitrogen tetroxide.
Let's see the calculation.
Okay, so it would be, it's just molar mass, right?
Molar mass.
Okay. It would be N equals 14.01 times 2 is 28.02. O equals 16.00 times 4 equals 64.00. Add 28.02 plus 64 92.02 versus 8.01 times N equals 14.01, and then 16.0 times 3 equals 48. So I stand corrected that the anhydrous nitric acid would be lighter, because it's
Let's keep going with that equation. So you figured out the molar masses, and you know the number of moles of each that you're going to need for the fuel. You got 1,908 moles, and you have 954 moles. So of your N2O4. So let's apply those against how many moles we're going to need of each. Which of these, when you multiply them out, 954 moles of N2O4, dinitrogen tetroxide, times the grams per mole, what's the total number of grams? This is where it can be a little bit tricky when you have more of something, but each unit weighs less. Makes it a little more complicated.
Yeah, I was kind of jumping the gun there.
Mm-hmm.
4, 6 times 92.02 equals 87829.41 versus 108.92 times 63.02. 2 times 63.02 1230.4. So yeah, I stand corrected again.
That's why we practice these, isn't
Yep.
it?
The dinitrogen tetroxide is definitely lighter.
Okay, so the dinitrogen tetroxide is much lighter by about a 50% factor, maybe not quite 50%, less weight than using the anhydrous ammonia or anhydrous nitric acid. Okay, so for weight, that is definitely our better choice. Now, we now know that we're going to use this number. Let's see, this is our number of moles that we calculated we need for the dinitrogen tetroxide, and this is the number of moles that we need for the anhydrous ammonia, or anhydrous, there I go with ammonia again, anhydrous nitric acid. And we can kind of look at these. And here's the density that we gave you. We need to know which one is going to require a bigger fuel tank. We want a smaller fuel tank so we have more room for cargo on this spaceship. Okay? We figured out the number of grams, right? That's
Yes.
what you figured out, the grams. You've already calculated those. And here we have the density. We have, for dinitrogen tetroxide, 1.44 grams per cubic centimeter. So we can figure out how many cubic centimeters it's going to take in order to contain all the dinitrogen tetroxide. And we have the density for the anhydrous nitric acid. So we can figure out how big the tank has to be for the nitric acid as an oxidizer. So we apply those densities. We have grams. If we divide by grams per cubic centimeter, we're going to get how many cubic centimeters our tank has to be.
And then we can just convert up here like what we did with the...
Actually, that because you will have it in cubic centimeters, and you can compare those two. A cubic centimeter is a unit of volume, and you'll be able to tell which of them will be the smaller volumes. Okay? So go ahead and divide each of those by the densities, and you can see the units will work out very nicely there.
Grams divided by, I don't know, 1.44.
Using density in a limiting reactant calculation is something that students haven't done yet, but it's something that within the next unit of gas laws they will be using within the combined gas law. So this is just kind of an introductory step getting into the next unit.
Did that wrong? 20300.14 divided by 1 equals 79668.97. So once again, dinitrogen tetroxide is smaller.
So we have roughly 61,000 grams. That's
The right unit.
cubic centimeters.
Oh, okay.
And here we ended up with about 80,000 cubic centimeters. So a difference. If you had to convert those when we started off, because we started off in liters, how would you convert this number of cubic centimeters and this number of cubic centimeters? How would you convert that back into liters?
Just move the decimal places over a certain amount of spaces.
Okay. So how many liters are we going to need for each of these?
It'd be what? 1, 2, 3. So it'd be roughly 61 liters for the dinitrogen tetroxide, and then roughly 80 liters for the anhydrous.
Okay, you got your numbers a little bit off.
Oh.
So let's take a look at those again. So you have, when you multiply, oh, okay, yeah. So you have the number of grams. You divide by the grams per centimeter cubed. You divide by that to get the volume, in order to get the centimeters cubed. So let's do those calculations.
So I flip them?
You multiplied here. And you actually, if you have the number of grams, if you divide, let me go and show you here. Just using unit analysis, you have a number of grams, and then you have grams per cubic centimeters. The grams will cross off. It'll leave you with the cubic centimeters. It'll leave you with the volume. When you multiplied, you actually multiplied here.
But it got smaller, and it was 80 something.
Let me see. Oh, did you divide there?
Yeah, it's a division thing.
Looked like you had it set up for multiplication.
No. Because that's 87,000, and the result gives you 6,000.
Okay. Just the way you had it set up there, it looked like you had multiplied it out. Okay, so we have the number of cubic centimeters. We talked about converting that into cubic meters, or into liters, so we can compare liters to liters. So that's pretty nice and simple. The dinitrogen tetroxide gives us a smaller volume and a lower weight. Okay, it's kind of looking forward to bridge into our next unit of gas laws.
Mm-hmm.
Now this is something that you haven't studied before, but let's talk about it anyways. So this is going to be rocket fuel. We want to get the video we watched talked about given the maximum amount of thrust, and that's in the form of heat and in the form of the gases that are expelled. So let's look at our balanced reaction. Okay, and this is another one that you have not seen yet, but I'm going to introduce it here.
It took me a moment to realize that there was 2 arrows in there.
When you see something in an intermediate stage,
mm-hmm.
it'll usually have an asterisk up over here.
Okay.
It means it's an intermediate stage. So it goes to an excited state before the final reaction actually occurs. So essentially, your reactants break apart into their component
mm-hmm.
elements, and then those component elements actually recombine. And in this case, we don't have any free oxygen, and we know for combustion reactions we have to have oxygen. So where does that oxygen come from? Let's just stick with the first one, since that's the one that is obviously most advantageous for space and weight. It actually comes from a liquid. We have the dinitrogen tetroxide, lots of oxygen in that liquid, but we have to have gaseous oxygen in order for the combustion to occur. So your hydrazine and your dinitrogen tetroxide actually instantaneously break apart into their components, and these are the excited states. That little asterisk means it's an excited
mm-hmm.
state.
You said that?
So it breaks apart into nitrogen and hydrogen and oxygen. We know nitrogen doesn't burn, but hydrogen and oxygen, when they get together, they burn really, really well. If you look down here at the second reaction, we have the same basic components. We still have nitrogen, we still have hydrogen, and we still have oxygen. And the hydrogen gas and the oxygen gas, when they get together, they burn really, really well. So let's look at the products of our reaction. So in this case, we have 3 moles of nitrogen, and we have 4 moles of basically steam. It's water in its gaseous form. So it acts just, once in its gaseous form, it reacts just like any other gas. So we are creating 7 moles of gases. Okay, let's look at our next at the other reaction. Let's look at the hydrazine, the same fuel, but using anhydrous nitric acid. Okay, it goes to its excited state level you talked about. But how many moles of gases do we produce from that reaction?
You produce 11?
We have 6 moles.
That one's not marked as a gas.
Sorry. Nitrogen is a gas.
Okay, I wasn't sure.
Okay, yep. So the nitrogen, just like there. So we're making 6 moles of nitrogen, 10 moles of water, and there's 1 mole of oxygen gas left over. So we're making 17 moles of gases. So taking that into account now, if we had to choose which one to use for the more efficient thrust, which one's going to create more gases going out the end of the rocket to give us more thrust, which one might you choose now?
Definitely the anhydrous nitric acid.
Because it gives you a lot more of the gases.
More than double.
It over doubles the amount of gases coming out. Now, there's also the factor of heat that is generated, and that's a couple months down the line, assuming that we actually go back to school.
I was going to say, I don't think we have time for that.
So that gets into thermodynamics. We may or may not get there during the school year, but you'll certainly get there if you take AP chemistry. That's one of the important fundamentals of physics and of chemistry to make sure that you're ready for when you go to college. So when you take the amount of gases calculated, you know what? NASA, it might actually behoove us to make a slightly larger fuel tank because we're going to get over double the amount of thrust, the amount of gases coming out. Yes, the fuel tank is a little bit large, but if you want to lift a heavier payload, a heavier satellite, that anhydrous nitric acid may actually be the better choice to give us more thrust because it's creating more gases, more products to give us more power. More power! All right, so given all that, when you take into account gas laws and how much gas is created, this actually may be the better choice. So now we're going to step one further. We're going to go to our extra credit problem.
Okay. So
read the extra credit problem.
Taking into account other chemical properties, which would you recommend?
So our 2 reactants that we can choose is dinitrogen tetroxide, and you saw in the video we watched on YouTube, it's a gas, but it's a gas at about 20 degrees Celsius, so about room temperature. It's a gas. You get it colder, put it on ice, it liquefies fairly easily. You don't have to have it at negative 200 degrees Celsius like you do for liquid oxygen or liquid hydrogen. So it's a lot easier to use that way. And then the other reaction is anhydrous nitric acid. It is naturally in STP standard temperatures, room temperature. Mm-hmm. It's a liquid. So both of these are fairly easy to use as far as making them into a liquid to put into the rocket, which is why they used them even back in the 60s. They were using particularly dinitrogen tetroxide, they got combined with hydrazine. That's what put the Titan rockets up into space.
And the Titan rockets were pretty dang big.
They were very big. But what about? So you saw this one today. Not too bad. The video that we watched. It was in a compressed cylinder. He cooled it down. There was no significant hazards associated with it. Anhydrous nitric acid.
Acids are corrosive.
Is a 24 molar acid. Really, 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 really strong acid. That's about as strong as you can possibly make an acid.
Dang.
So when you take that into account now, unless you have very secure ways, very safe fuel tanks to be able to load up a rocket that's going to take some G's and it's going to be shaking all over the place, you don't want 24 molar nitric acid eating away at parts of your spaceship. So Which one do you think you would want on your spaceship?
I would still definitely go with the dinitrogen tetroxide, just because even though there's the more thrust and the anhydrous nitric acid, everything else about it is like not good.
Yeah, so there is a risk, and that's where they have to look at what is the system design. Can we make a fuel tank that's not going to get chewed away by that incredibly strong acid, that can still be flexible, and the fuel tank itself doesn't have to be so heavy that we're needing more thrust than the extra thrust is giving us because of the extra weight that's going to be able to safely manage that strong of an acid.
What's like the strongest acid level that you could possibly make?
That's it.
24, not 25 or anything like that?
Well, you can get up to about 30 moles per liter in some of the less some of the more dense acids. You can get up to 30s, I think, the highest I've ever seen. But really, it's almost irrelevant at that point.
Mm-hmm.
It is incredibly dangerous stuff.
Mm-hmm.
And obviously, we all remember the Space Shuttle Discovery when she went up in smoke.
That was going to be one of my next questions. Which one were the ones that went wrong?
Okay, that was actually that was a liquid fuel that happened on that one. The solid boosters, even after so on the Space Shuttle Discovery, looking at the top down, you had the space shuttle, then you had this big central fuel tank, and then you had the two solid boosters on the side of that.
Mm-hmm.
The solid boosters, even after the big fuel tank here exploded, you can still see the solid boosters. They kept going. They kept burning and kept going.
Okay, so weren't the ones that like whoosh off in different directions?
They went off and they spiraled off and went off in directions. It was actually the liquid fuel tank here that had the problem, where the fuel, a gasket on one of the fuel lines, a rubber gasket.
Yeah, I was gonna say it was something really small.
Yeah, it was literally a rubber gasket that was supposed to connect two pipes together.
Mm-hmm.
The rubber gasket failed, partly because of the temperature of the fuel, some of the liquid oxygen, liquid hydrogen. In our video, they talked about cryogenic fuels, super duper duper cold fuels, liquefied oxygen and liquefied hydrogen. Those are below 200 degrees Celsius. They're cool. Very, very cold. What happens to rubber when it gets cold?
It gets really stiff and hard.
It gets very hard, and when it's hard, it breaks. One of the fun things that I've seen done in chemistry classrooms, you take a rubber
stress ball?
No, you take a racquetball.
Okay.
So it's a little bit smaller than the size of a tennis ball.
Mm-hmm.
No foam covering on it.
Mm-hmm.
No little fur.
Yeah, I think I know.
It's just a rubber ball. You put it in liquid nitrogen, which is 170 degrees below zero, and then you leave it in there for 30 seconds, and you pull it out, drop it on the desk.
I'm guessing it cracks.
Shatters. It's like glass. It's so hard that the rubber is turned into effectively like glass. It just shatters into 1,000 pieces. So when you have rubber gaskets, when you have those colder temperatures like oxygen and nitrogen liquefied, also very, very, very cold, and that's where you have problems. So the same things where we talked about where, you know what, you can have a great fuel, but it has side effects. It has its downsides. So what type of rubber can you use for that gasket that's not going to be eaten away by 24 molar nitric acid? So the same kind of problems, just more of a chemical property than the cold physical properties of liquid nitrogen and liquid hydrogen for cryogenic fuels. So, what are you going to tell NASA? NASA came to you for answers. What are you going to tell them?
Go with the dinitrogen tetroxide fuel. It's a lot less dangerous and lighter and cheaper and all these good things.
All right, that sounds good. All right, good job, Rebecca.
Thank you.